Hello everyone, welcome to the electromechanical devices course. In the previous meeting we discussed the series and parallel equivalence method for the network analysis or electrical circuit analysis, and again the focus of this chapter 2 in the textbook is to cover the resistive circuit analysis. And we explained before that we are going to cover 4 methods of the network analysis or resistive circuit analysis. And these 4 methods, basically the Kirchhoff voltage law, current law, and Ohm's law. This is the first method is just to use these 3 laws to do resistive circuit analysis. And the second method is series and parallel equivalency, just to calculate the equivalent resistance and use this equivalence to do electrical circuit analysis. And we already covered these 2 methods in the previous lectures. In today's lecture, we are supposed to cover the 2 methods, the node voltage analysis and the mesh current analysis. In this video, I'm going to discuss the node voltage analysis and how we can use this method for network analysis or electrical circuit analysis, especially the focus again over the resistive circuit analysis. Okay. So very quick, what is node voltage analysis? Node voltage analysis and the electrical circuits design, basically the node voltage analysis is a method. It is a method, as I said, of electrical circuit analysis, and basically it depends on you and determining the voltage differences between 2 nodes within an electrical circuit in terms of the branch current. Like there are 2 main information that are essential to use this method basically. First, we should have an idea about the voltage over each individual node, and we're gonna give a name to the voltage over the node as voltage node. And if we calculate the difference between these node voltages, we're gonna end up with an element voltage. So there are 2 terms that we have to distinguish here through this method basically. These two terms, the first term is the node voltage and the element voltage. They are different. There is node voltage and there is element voltage, as we are going to discuss. So once we calculate the difference between the node voltages, we gonna come up, or we gonna find an element voltage. Then if we do have the current over this element, we can form some equations. And then we can use these equations to find the unknowns. And as we mentioned before, to find the unknowns, it means that you're already doing electrical circuit analysis. It means, or in other words, to do electrical circuit analysis, it means just to find the unknowns. And this unknown, it would be resistance, it would be currents, or it would be voltage. But we said that the focus in this course is to do analysis. And in the word analysis, it means that the unknowns, it should be either voltage or current. And in all of the cases, or in many cases, the resistance will be given. So node voltage analysis is a general method of analysis that can be applied to any electrical circuit. In some cases, if the other methods, especially the first 2 methods that we covered, which are the Kirchhoff voltage law, current law, and Ohm's law, or the series and parallel equivalent, if these 2 methods, or if you find that it is difficult for you to do electrical circuit analysis using these 2 methods, so the best option for you will be the node voltage analysis method. Okay, and this is what we are going to discuss through today's lecture. All right. So how it works basically, there is a general procedure. First of all, I'm just gonna explain this general procedure for the node voltage analysis method, which consists basically of 8 steps. So in step 1, for example, is just to locate nodes in an electrical circuit. Assume that you already given this electrical circuit, and again you find that it is difficult for you to use the first 2 methods to do electrical circuit analysis for this circuit. So the best option, as I mentioned, for an electrical circuit with this arrangement, with this shape basically, is just to use the the node voltage method. Okay, so how it works, the first step, as I mentioned, just locate nodes within the electrical circuit. We defined before the node that it is this is like the intersection, or the point of intersection between the 2 or more electrical elements within an electrical circuit. So this is an electrical circuit, and this electrical circuit consists of so many nodes, of so many elements. We do have the voltage source, this is one electrical element. We do have this resistor with resistance R2, this is another electrical element. We do have another resistor, another resistor, another resistor, another resistor. So all of these are different electrical elements that form or arranged in somehow, in some way, to form this electrical circuit, right? The intersection of any two or more, the intersection of multiple or different electrical elements that do intersect together or meet together at a point, this point is a node, as we discussed before, right? So your objective in step 1 is just to locate these nodes. Where are the nodes within these electrical elements? And just give number, whatever this number. For example, we do have here one node, which we're gonna give it like node 1. Then we do have node 2, we do have node 3. Node 1, this is an intersection between 3 different electrical elements within this electrical circuit. We do have element 1, which is this resistor. We do have element 2, which is the voltage source. And we do have element 3, which is the R1. Node 2, it is intersection also of 3 elements. We do have this resistance R2, R3, and R4. So node 2, this is the intersection of these 3 elements. Node 3, this is the intersection also of 3 elements, which are R3, R5, and R1. Make sense? Also, there is another node, which is this node. For example, this node, it is the intersection of the voltage source, Vs, and the resistance of R4 and the R5. All of these 3 elements, they do intersect at one node, which is this node, which we're already giving it a name here as reference node, and we're going to discuss this point. Forget about the name for now. You should understand there is a node here, okay? So the node, basically, again, this is the intersection point between different elements. Another point or another thing that you should understand here, that any electrical element, it should has 2 nodes. It should have 2 nodes. Like, for example, this electrical source, this voltage source, it has 2 nodes, which are the node 1 and this reference node. Make sense? How about this resistor? It has 2 nodes, like 2 ends. Any electrical element should have 2 ends, 2 nodes. Node 2 and the reference node. For this one, it has 2 ends, node 1 and node 2. This element has 2 ends, node 3 and node 2 and node 3. This electrical element R1, the resistance R1, it has 2 nodes or 2 ends, node 1 and node 3. R5 has 2 ends from the reference node and the node 3. Make sense? So your objective in step 1 is just to allocate all of these, or locate or define all of these nodes. So we do have V1, V2, V3. There is another node, you can give it a number like 0 for now. Make sense? Then step 2, select a reference node. Pick one of these nodes that you defined. Here we defined 4 nodes in total. Node 1, 2, 3, and the 0 node. Pick one of these nodes to be a reference node. What is the reference node? You could consider this is your reference. This is the 0 point. And you're going to assume, we are going to assume a 0 voltage with respect to this node. And basically, in many of the cases, it is preferred to have one of the ends of the voltage source to be the reference node. So again, it is preferred to have one of the ends of the voltage source to be the reference node. So for example, if I ask you what is the voltage source in this electrical circuit, we do have, this is the voltage source, which is Vs. It has 2 ends. One end that is located at node 1, and there is another end that is located at node 0. So pick one of these 2 nodes to be the reference node, and it is preferred to have this node that is close to the ground. This is like the ground of any electrical circuit, right? So that is close to the ground to be the reference node. Make sense? So this is our reference. Assume that this is going to be our reference, but you can choose any other node to be the reference, but it is preferred to have one of the ends to be a reference node. Once you specify or define the reference node, you are going to assign node voltage. This is the new keyword here, the node voltage. So what does it mean, a node voltage? This is the voltage at each individual node. Like we do have here a node, so there is a certain voltage value at this node. We do have another node, it has a certain value of voltage. The same thing, node 3, it has a voltage, and so on. So your objective is just to assign voltages at all of the 4 nodes. We here located 4 nodes. So I'm gonna consider that I do have V0 at the reference node. I'm gonna assume that I do have V1 at node 1, and there is voltage at node 2, V2, and voltage at node 3 as V3. But you should understand that V0, V1, V2, V3, these four voltages, this known as the node voltages. Make sense? Once you assign these node voltages, you can move to the next step. The next step basically is just to locate the elements within the electrical circuit. So step 1 is just to allocate the nodes. Define the nodes. Step 2, define one of these nodes that you selected or defined or allocated. One of them, it should be the reference point. Step 3, just assign voltages to all the nodes. Make sense? How about step 4? Step 4 is very simple. Locate the elements. How many elements? And locate these elements within this electrical circuit. So in total, we do have one element, which is the voltage source. We do have another element, which is resistor with a resistance R2. Another element, another element, another element, another element. So in total, we do have 5 elements within this 1, 2, 3, 4, 5, 6 elements within this electrical circuit. One of them is a voltage source, the other are resistors, right, with different resistance. So your objective in step 4 is very simple, just locate these different elements. So we already located all of these elements. Step 5 is to assign element voltage. So element voltage, it is different than the node voltage that we defined before. This is a node voltage. But here now we are talking about the element voltage. The node voltage that we defined is different than the element voltage. So what is the element voltage? So for example, we defined here V1, right? And the voltage here was V0. And we defined here another voltage as V2. And there was here V3. So V0, V1, V2, V3, these are the node voltages. These are the like V1, this is the voltage value at point node 1. V2, this is the voltage at point, which is node 2. V3, this is the voltage at another point, which is node 3. V0, this is the voltage value at the reference point, which is the reference node. Make sense? But how about the element voltage? For example, if we choose this element, the voltage over this element, it should be the difference between the voltages at its nodes. For example, the element 2 with resistance R to this element, it has two ends. One end is located at node 1, the second end is located at node 2. So the voltage here is V1, voltage here is V2. So the difference between these two voltages, V1 negative V2 or V2 negative V1, this should give us the voltage over this element, which is known as the element voltage. So in general, the element voltage, this is the difference between the node voltages at two nodes. V1, it is a node voltage. V2 is a node voltage. Vy, this is the voltage over this electrical element. Vx, this is the voltage over this electrical element. Make sense? Vz, this is the voltage over this electrical element. So your objective is just to assign element voltages. For each element, give a voltage value, right? And you should understand that this voltage value, as we are going to explain next, is gonna depend on the difference between the node voltages at the two ends of this electrical element. So there is a difference between the node voltage and the element voltage. Make sense? So for this electrical element, for example, I'm going to assign Vy. For this electrical element, I assign Vx. Here I assign Vz. What about the directions? The direction of this Vy or Vx or Vz, assume any direction. That is fine to assume Vy moves from 1 to 2 or 2 to 1. It's up to you. You can, initially, we have no clue how much is V1, how much is V2. So initially, we assume we give any direction. So give any direction for Vy, give any direction for Vx, give any direction for Vz. This y, Vx, Vy, Vz, just give any name, give any symbol. For example, I can give this one as VR3. I can give a name to this one as VR2. I can give a name to this one as VR1. So also there is one voltage here, the voltage source, right? This is an electrical element. It should have a volt. There is another electrical element here, it should have a volt. There is another electrical element here, it should have a volt. But let us discuss this volt, for example, or this one, these three vertical voltage elements, right? The vertical elements here, like the voltage source, this resistor, and this resistor, they are moving between, they have two ends, each one has two ends, like two ends from V0 to V2, or V2 to V0, as we mentioned, assume any direction, right? So, for example, for this electrical element, it has two ends. One of these two ends is the reference node. This is the reference node, right? One of these two ends is the reference node. It is advised, in case that you do have an electrical element and one of its ends is the reference node, to assume the element voltage that moves out of the reference node, like moves from the reference node to the other node, like R4. Its voltage direction, I'm gonna assume that it moves from V0 to V2. For example, R5, it has two ends, V0 and V3. So I'm gonna assume that it comes from V0 to V3. How about the voltage source? The same, it has two ends, V0 and V1, so assume that it comes from V0 to V1. It is preferred, but that is fine if you switch. But in terms to make the calculation simple, it is preferred to assume that the voltage element for any of the electrical element that has one of its ends is the reference node. So assume that the voltage element or the element voltage moves out of this reference node. It moves from the reference node to the other node. Make sense? And you can give any names to these voltage element voltages. Make sense? You can give, for example, like VR1, VR3, VR2, VR3. I can give, for example, here VR5. Here I'm gonna have like VR4. Then I'm gonna have here like VS. Make sense? And you should understand that VR1, VR2, VR3, and VR4, and the VR5, in addition to VS, all of these voltages, these are the element voltage, not the node voltage. Make sense? And this is the objective of step 5. So as you can see, we didn't do any calculation. We didn't do any write any equations or do any calculation. The key idea is just to set up the node voltages, the element nodes, locate the nodes, locate the element. This is for the first 5 steps, very simple. As for the next step, which is step 6 basically, and that is very important, is to determine the element voltage in terms of the node voltage. We said that we do have element volt and we do have node volt. So your objective for each element, for every element within this electrical circuit, is just to define its element voltage in terms of its node voltages. Make sense? So how we can define this basically, as I mentioned above, that for example, here I assume that this one, I assume that it should be VR1, this should be VR3, right? And this should be VR2. And this like VS, which stands for the source. And we do have here VR4, and we do have here VR5, right? So these are the different element voltages that I defined in the previous step, right? So each one of these element voltage, it depends on the voltage at its two nodes. Like here, we do have node V1, we do have node V2, we do have node V3. Here we have the V0. We can assume that V0 is just 0. This is our reference. Like just set this value into 0, right? So we're gonna have 4 nodes. Your objective is just to find VR1 in terms of V1, V2, V3, V0. The same thing VR2, VR3, VR5. It means that you in step 6 is just to write an equation for each one of these element voltages in terms of the voltages of its nodes. Very simple. How we can do it? It is very simple step. For example, let us assume that we do have any electrical element. This electrical element, it would be resistor, capacitor, whatever it is. And we assigned or specified or defined an element voltage, Vx. This is the element voltage. This is the element voltage. Right? And this should be the node voltage. This is a node voltage. and this is another node voltage, right? Node voltage. So what we did basically, we defined Vx as an element voltage, and we do have Vn, Vk as two node voltages. So how much is Vx in terms of Vn and Vk? I assume that Vx moves from K to N. So Vx, it should be the difference between Vn negative Vk. You're just gonna invert the direction, switch the direction. If you're moving from K to N, so it's gonna be N negative K. Very simple, as given here. So Vx, it will be Vn negative Vk. How about if you assume the opposite direction? So you're gonna say that Vx equal Vk negative Vn. Very simple. Make sense? So if we apply this, for example, to VR, let us start with VR3. VR3, this should be like VR3 according to my new definition to the different electrical elements. So VR3, it should be, it moves from V3 to V2. So it should V2 negative V3. So it is V2 negative V3. How about VR2? VR2, it moves from V1 to V2. So it should be V2 negative V1. V2 negative V1. How about VZ, which it should be VR1. VR1. VR1, it moves from it moves from node 1 to node 3, because I'm moving in this direction. It moves from 1 to this direction. Basically, looks like you're already moving in this way, right? Like you're already moving from 1 to 3. So this is the direction. You can assume, for example, we can write this one in this way, like it's still the same direction. I'm not rotating in a complete circle. I'm just jumping from node to another node. I'm jumping from node 1 to node 3. So this should be V1 to V3, so it should be V3 negative V1. So it is V3 negative V1. Make sense? So this is for these three element voltages. How about this vertical element? For this vertical element, it should have like VR5. If I ask you, let us start with VR4. VR4 is going to be simple. VR4, which is this vertical one, it moves from V0 to V2. So it should be V2 negative V0. And remember that we assume that this should be 0. So this is going to give us V2. So that's why initially I give in here, before this one, if we remove this one, initially I wrote directly here V2. This explains why this value was written as V2, right? So automatically, if you have an electrical element, one of its ends is the reference. So assume the direction of this electrical element moves from the reference to the other node, and assign the element voltage to this element to be the same voltage value of its other node voltage. Like for example, this one moves from 0 to V2, so its element voltage automatically will be V2. Like this one, this electrical element, which is the voltage source, it moves from a reference point to another node, so automatically it's going to take V1. This one moves from 0 to V3, so automatically it's going to take V3. It means that VR5, automatically VR5 will equal to V3, and the same thing for VS. You're going to find that VS here, it will equal to the V1. So this explains why I set in the beginning V1, V2, V3 over this vertical element. Why? Because one of their ends is already the reference node, which is we assume that it has 0 voltage. Make sense? So this is for step 6, is just to determine the element voltage in terms of the node voltage. This is very simple for step 6. Then you can move to the next step, which is step 7. Step 7, we're almost there. We still have just 2 steps, step 7 and step 8. In step 7 is just to write Kirchhoff current law equation, or Kirchhoff current law, in terms of the node voltage for each node, or for each node, for every node. For example, we look at it for this electrical circuit, 4 nodes, right? This is node 1 with voltage V1. This is a node 2 for voltage V2. This is a node 3 for voltage V3. And we do have the reference node, which is V0. Intuitively, since the voltage over this node is 0 and this is our reference, you shouldn't write, or there is no need to write a Kirchhoff current law to the reference node. It means that you're gonna write Kirchhoff current law to all the node except the one with the reference node. There is no need to write the Kirchhoff current law to the reference node. because this is our reference, okay? So what does it mean? It means that we can write a Kirchhoff current law to node 1, node 3, and node 4. But let me refresh your mind or remind you with the Kirchhoff current law. Kirchhoff current law states that the sum of the currents over any node, it should be 0. This sum, it means that we're gonna collect all the currents that enter the node. It should equal to all the current that leave the node, right? This is the very simple, the Kirchhoff current law. So for example, let us start with node 2, which is this node. So how many currents? Remember that we didn't distribute the current over this electrical circuit, right? But let us assume that there is a current here over this electrical circuit, so it should come and move in this direction. Why? Because we assume the voltage element moves in this direction. So we're gonna consider that the current goes in the same direction as the voltage element or the element voltage that we assumed. The same thing, this element voltage Vx moves in this direction. So it means that we're gonna have a current that goes in this direction. So these two currents will be entering the node. The same thing for this element voltage, which is V2, we're gonna have like a current goes also to the same node. So as you can see, this node is an intersection of 3 electrical elements. So that's why this node, it will collect, or it will depend, or the current law for this, the Kirchhoff current law for this node will depend on 3 currents. 3 currents, why 3 currents? Because we do have, it is intersection of 3 elements. Each element will have its own current. It makes sense? So we do have 3 currents and all of them are entering the node. So if we sum all of them, on the left side, the right side, it should be 0. This is the Kirchhoff current law for this node, which is very simple. But if I ask you how much is the current over this electrical element, we don't know. We didn't assign a current. In the previous 2 methods, and this is what we explained in the previous lectures, the first step was just to distribute the current through the electrical elements. Here we didn't distribute the current. So we have no clue, we don't understand, we don't have a value, we didn't assign a value for the current over R2, the current over R3, or this resistor or this resistor. But how we can find the current in terms of voltage or resistance? This is according to Ohm's law, right? So according to Ohm's law, if you remember, that Ohm's law states that the voltage over any resistor equals the current times its resistance. The current over this resistor times its resistance. So according to Ohm's law, if I ask you how much is the current over any resistor, it should be the voltage over the resistor divided by its resistance. So here, for all of these resistors, for all of these electrical elements, I do have a voltage element or element voltage and resistance for each one. So if you divide V over R, this is gonna give us the current over this element. If you divide Vx over R3, this is gonna give us the current for this second element. If you divide V2 over R4, this is gonna give us the current over this element. Make sense? So if I ask you to write the voltage, the current Kirchhoff law to node 2, so the Kirchhoff current law to node 2. How many currents? We do have 3 currents and all of them are entering the node. So we do have the first current, which it should be Vy over R2. Agree? According to Ohm's law. So this is the first current. It should be Vy over R2, Vy over R2 plus, because this one enters also, Vx over R3, Vx over R3 plus V2 over R4, V2 over R4 equals 0 because there is nothing leaves the node. Very simple. Make sense? So here the different thing that we just wrote the current in terms of its voltage and resistance for the same electrical element. This is for node 2. If I ask you to do the same for node 3, how about node 3? Node 3 is intersection of 3 elements also. So it should have like 3 currents. One element, which is this one, but the current of this element leaves the node. There is another element, which is this one, the current of this element entered the node. It already entered the node, right? It goes to the node. The VZ direction, it goes to V3. And there is another current which is also entered the node. So there is one current that leaves. there is one current that enter, there is another current also that enter the node that comes from the element R1 according to this direction. It entered the node, goes to R3. Make sense? So, so if we decided to write the Kirchhoff current law for node 3, Vz enter the node, Vz over R1, Vz over 1, this gives this current which is already entered the node, so that's why it is positive. But Vx over R3, there is another current which just leave the node. So anything that leave the node, you do have two options, either to put it negative or just write on the just put it on the right hand side. It's gonna be the same result, the same equation. If you simply you just gonna put it negative here because it leave the node, plus V3 over R5, it entered the node, so it should be positive, equal 0. Make sense? So we applied the Kirchhoff current law to node 2, we applied the Kirchhoff current law to node 3. Make sense? How about node 1? As we agreed that we won't gonna write, we will not going to write a Kirchhoff current law to node 0 or to the reference node. There is no need to write the Kirchhoff current law to the reference node because it is our reference as we mentioned and it has 0 voltage. But we do have 3 other nodes. We wrote the Kirchhoff current law to node 2, we wrote the Kirchhoff current law to node 3. How about the node 1? Node 1, we won't gonna able to write a Kirchhoff current law to node 1. Why? Because one of the elements, node 1, it is the intersection of 3 elements. One element is resistor, the second element is resistor, the third element is a voltage source. A voltage source, it means that basically we won't gonna have an idea because we didn't assign a current in the beginning, right? So we don't know how much of the current over this voltage source unless we apply Kirchhoff current law or Kirchhoff voltage law in a different, but we should have information of the other electrical elements. It means that in this node voltage method, in this method, if you have if there is a node and this node is one of the ends of a voltage source, so skip this node and don't apply the Kirchhoff current law to this node. So in the beginning, I'm gonna ask myself, how many nodes? I do have 4 nodes. The reference node, there is no need to write Kirchhoff current law to this node, so I'm gonna skip V0. Then node 1. For node 1, it is one end. It is one end of a voltage source, so I'm gonna skip this one too. Then you're just gonna end up with 2 equations. You're gonna apply Kirchhoff current law twice just for node 2 and node 3, so you're gonna end up with these 2 equations. Once you solve this equation, you should find everything in this electrical circuit. Make sense? But as you can see, we wrote this equation for node 2, this equation for node 3 in terms of the element voltage, Vx, Vy, Vz, these are the element voltage. Then your objective is just to replace the element volt by its node voltage here. For example, if I ask you how much is Vy in terms of V1 and V2, it moves from V1 to V2, so it should V2 negative V1. So you're just gonna substitute for Vy with V2 negative V1. How about Vx? Should be the same. It moves from 3 to 2, so it should be V2 negative V3, V2 negative V3. How about V2? Just V2, because the voltage over this element is just V2. Very simple. So you're just gonna rewrite again this equation, but in terms of the voltage nodes. The same thing for the third node or node 3, Vz. I already have Vz. It moves from 1 to 3, so it should be 3 negative 1. Vx, it moves from 3 to 2, so it should be 2 negative 1. V3, it should be just V3, right? So you're just gonna end up with 2 equations. As you can see, these 2 equations has 3 unknowns. These 3 unknowns are V1, V2, and V3. Make sense? V1 definitely will be given. Why it will be given or it will be known? Why? Because V1, it should be the same voltage at the source. Because V1, this is the voltage over this element. And this element by itself, this is the voltage source. So what does it mean? It means that V1 equals Vs. It means that V1 is already given. So you're just gonna end up with just 2 unknowns, which are the V2 and V3. That's why you have 2 equations. If you solve these 2 equations, and this is the step 8. Step 8 is just to solve the equation that you got for the voltage for the node voltage, just to find the node voltages V2 and V3. Once you find these two node voltages, you can find any other information depending on the requirement of this electrical circuit. But these steps, the 8 steps, are fixed. Then once you finish this step and find the node voltages, you're just gonna look to the problem, see the problem, what are the requirements, and start to work on finding these requirements in terms of the voltage, the node voltage that you just got by solving these two equations. Make sense? So this is the general procedure of the node voltage analysis method. There is an important note here that the number of the required equations equal the number of the unknown unknown node voltages. Like for example here, within this electrical circuit, we do have 4 node voltages. V0, and we already have this value, it is already 0. V1, which should equal to the Vs as we explained. So we have only 2 unknown node voltages, which are V2 and V3. So you should find 2 equations. Make sense? So the number of the equations, it should equal to the number of the unknown node voltages. We do have in total 4, but we have just 2 unknown. So that's why we need just 2 equations. Make sense? So this is the general procedure of this method. What I'm gonna do now, I'm gonna give you 2 examples. I'm gonna solve 2 examples with you as demonstration over this method. So if we consider this example here, what would the first step? If you're gonna see as an electrical circuit with this shape, basically, it means that intuitively or directly it is preferred to use the node voltage analysis method, because it's going to be preferred over the other method, especially the equivalent resistance, because you would find it is difficult for you to find the equivalent resistance for this electrical circuit. Okay, but anyway, we can find it, but it would be somehow difficult, but that's why it is preferred to use the node voltage analysis method. Okay, so how it works as we explained. What was the first step? The first step is just to locate the nodes, find the nodes within this electrical elements. So first of all, we do have this node, right? This node is an intersection between 3 elements. The first element is this voltage source with a voltage value which is given by 25 voltage, and we do have the other electrical element which is R1 with 5 ohms, and we do have the other electrical element which is resistor of resistance R2 equals to 10 ohms. Make sense? So this node, you can give number to this one as node 1. And we do have another node which is going to be like node 2. Then we're going to have another node like node 3. Then we do have node 0. This is the 0 node. This is the reference node as we agreed, right? So we do have in total like 4 nodes. We're gonna choose this one as a reference node. Why? It is end of the it is one of the ends of the voltage source. It is one of the ends of the voltage source, and it belongs to the ground, because the ground of this electrical circuit, it should be located here. So it is preferred to have this one as the reference node. Make sense? So the first step is just to locate the node, we located them. The second step is just to assign or specify or define a reference node, and we did. This is gonna be our reference node. Make sense? Then the third step is just to assign voltage for each node. I'm gonna give a voltage node here like V1, V2, and V3. Make sense? I'm gonna give a voltage node for all of these nodes like V1, V2, V3, and this should be like the V0, which it should be 0 as we discussed before. Make sense? So this is the third step. How about the fourth step? Fourth step is very simple. Locate the elements. How many electrical elements do we have here? We do have the voltage source. This is one element. We do have this resistor. We do have another resistor, 6 elements within this electrical circuit. All of these are different elements, and this is step 4. Just locate the element. Step 5, assign element voltage. For each one of these elements, give a voltage. But this voltage should be element voltage, not a node voltage, right? So for example, I can give to this element like voltage, I'm gonna give it a name like Vy or Vx, whatever it is, like Vx for example. Make sense? Or let us assume Vy, just stick to what we did before. Then how about this electrical element? I'm gonna give it a voltage like in this direction as Vx. Why I'm giving this direction? As we mentioned, assume any direction. You can assume even Vy goes from 2 to 1, not from 1 to 2. The same thing, Vx, you can assume in the opposite direction. It's up to you. Just give any direction, give any name. So Vy, this is the voltage for this electrical element. Vx, this is the voltage for this electrical element. How about this electrical element? I'm gonna give another voltage for this electrical element like Vz. For this one, like Vz. Where Vz, it moves from 1 to 3. You can assume the opposite direction. It's up to you. So I assign a voltage for this element, I assign a voltage for this element, I assign a voltage to this element. How about these three vertical elements? This one, this is a voltage source. It has one of the ends at the reference. So automatically the voltage, it is preferred to be assumed moving from the reference going to the other node over this electrical element, and automatically is gonna take the same voltage of the other node because the reference is already 0. Make sense? The same thing works for this vertical node. It moves from 0 to V2, so it's gonna take a voltage directly as V2. How about this one? The voltage over this element will be automatically V3. Why V3? Because the reference is already 0. So it's going to be V3 negative 0. So that's why I'm giving V3. So if you assume the direction of the voltage over any element that it has end, that is the reference node, it should move from the reference node to the other node, and its element voltage, it will be the other node's voltage. Make sense? So here, and this is for step 5, it's just to assign. Step 4 to locate the element. Step 5 is just to assign the element voltage to all of these elements. How about step 6? It's just to find, and this is the first thing that we are going to write here. Find the element voltages in terms of the node voltages. This should be step 6, right? So how we can just write these electrical elements. So if I ask you, for example, how much is the voltage over this element, there is already V1. So there is no need to write an equation for V1 for this electrical element. How much is the voltage over this one? It is already V2. It is already in terms of V2. How much is the voltage over this element? It is already V3. But how about Vx, Vy, Vz? These three elements, we have to find Vx, Vy, V3 in terms of the node voltages, which are V1, V2, and V3. So if I ask you how much is Vy? How much is Vy? Let us use a different color. So how much is Vy? Vy, it moves from 1 to 2, so it should be V2 negative V1. Make sense? How much is Vz? So it moves, Vz, it moves from 1 to 3, so it should be 3 negative 1. So it should be V3 negative V1. If I ask you how much is Vx, so Vx, it moves from 3 to 2, so it should be like V2 negative V3. Make sense? And this is for step 6. How about step 7? Step 7 is just to apply, and this is the most important step basically, is just apply the Kirchhoff current law to different nodes. So in this electrical circuit, how many nodes do we have? We located 4 nodes. One of these nodes is the reference node. There is no need to write Kirchhoff current law to this node. We have other 3 nodes. How about node 1? We're gonna skip this node. Why? Because it is an end of a voltage source. So we will not be able to write the current law, the Kirchhoff current law to this node at the moment, right? So we're gonna skip this one. Why? It is an end of the voltage source. So we still have to write the equation for V2 and V3. Or in other words, for node 2 and node 3, so we're gonna write 2 equations. In addition, as you can see, V1, it is already given by 25 voltage, right? It is already given. So we have only 2 unknowns. How much is V2, how much is V3? We have no clue. We said that V1, because the voltage over this electrical element, it is given by 25 volt. So, and the voltage, according to our arrangement and our setup of these electrical elements, we specified V1 to be the voltage over this voltage source, which is already given by 25. It means that V1 automatically equals 25. So it means that you already have a value for V1, but we have no clue how much is V2, how much is V3. So we need just two equations, I'm sorry, because these are just two unknowns, so we just need two equations. One equation is going to be for node 2, the second equation is going to be for node 3. Make sense? So if I ask you about the Kirchhoff current law to the node 2, so for node 2 we do have Vy enters, V2 enters, and Vx enters, or there are three currents, and the three currents already, all of them already enter the node 2. Make sense? So if I ask you to write the Kirchhoff current law to this node, you're gonna find, if I ask you how much is the current over this resistance, it will be Vy over R2, right? How much of the current over this resistor? It will be V2 over R4. How much of the current of this resistor? It will be Vx over 20. And all of them should be summed. So we're gonna end up at the end for node, this is gonna be for node 2. So we're gonna end up with the first current will be Vy but over R2 plus it enters, plus there is another current which is V2 over R4. Make sense? V2 over R4 plus the third current which is Vx over 20 or over R3. So it should be Vx over R3. It should be 0, and this is gonna give us the first equation. Okay, then we can rewrite again this equation, but in terms, we have to make sure that to replace all the element voltages in terms of the node voltages as we did in the previous step. So for example, how much is Vy? We got it by V2 negative V1. How much is Vx? We got it by V2 negative V3, but we just gonna carry on the V2 as it is. So we can rewrite again this equation in terms of V2 negative V1 over R2. How much is R2? R2 is already given by 10 ohms, so it should be 10 here in the denominator, plus V2 over R4. How much is R4? R4 also is given by 10 ohms, so it's gonna be 10 plus Vx. We got Vx here by V2 negative V3. V2 negative V3 divided by the R5, which is already given by, Vx by R3, which is already given by 20. So it is 20 equals 0. Make sense? As you can see, to solve this equation, we have to multiply. It is better to multiply all the terms times the biggest or the max, the highest denominator value. The highest denominator value here is 20. So multiply all of these terms times 20. So this is gonna give us like 2. We can rewrite again this equation into like 2V2 negative V1 plus 2V2 plus V2 negative V3 equals 0. Make sense? So we can arrange this equation. It is better to arrange this equation into a coefficient into like V1 plus or minus or plus V3, V2 plus V3 in their order. Like for example, we're gonna have here like and remember, you can even substitute for V1 because we already have a value for V1 as we discussed. V1 is already given here, right? So I'm gonna give a value for V1. It is already given by 25 voltage. So it means that we're gonna end up here with negative 50, right? Plus we're gonna have 2V2 plus 2V2 plus V2. So this is gonna give us in total like 5V2 negative V3 equals 0, and this is gonna give us the first equation. Make sense? How about the second equation? We're gonna do the same, repeat the same procedure, but for node 3. As for node 3, which is this one, it connects three elements. One element that entered the node with a current, its current entered the node, which is Vz over R1, and V3 over R5, it also entered the node, but Vx, it leaves the node, right? So we're gonna have an equation for node 3. We're gonna have here like Vz over R1 positive, enter the node, Vz over R1 enter the node, plus There is another current that entered the node, which is V3 over R5, V3 over R5, negative. There is only one current that leaves the node, which is Vx over R3. Vx over R3 equals 0. Then substitute. How much is Vz? We got it before. Vz, V3 negative V1. So it's going to be V3 negative V1 over R1. How much is R1? R1 is already given by 5. Then how much is Vx? It is V2 negative V3. And R3 is already given by 20. So this one is 5. So it's going to be like over 5 plus V3 over 20, which is R5 negative Vx, which is V2 negative V3. This should be divided by 20 equals 0, right? Vx, it should be V2 negative V3, and it is 20 and 20 here. Okay, then you're gonna multiply all the terms times the highest denominator, which is 20. So we're gonna end up with 4 here. So this is gonna give us 4V3 negative 4 times 25, because we already have V1 equals 25, plus V3 negative V2 plus V3 equals 0, right? So this is going to give us another equation. If you summed here, you're going to end up with like 5V3 negative 100 plus negative V2 equals 0. And this is going to give us the second equation. Make sense? So we end up with 2 equations. You can solve them even using calculator, whatever the way that you're going to solve these 2 equations. Very simple equation to be solved. We're going to end up with that V, if we solve these 2 equations, solving the equations. Okay, let us. So if we solve these 2 equations, we're going to end up with like in 2 unknowns, which are the V2 and V3. So we will find the V2 will equal to 13.8 volts, and the V3 will be 18.97 volts, which is going to be like around, you can just assume that this is 19 volt. That is fine. Okay, so we end up with these 2 node voltages, and that's it. But remember, what is the requirement? What was required in this equation? Okay, how about if it is required from us to find IB? IB, this should be the current over this electrical element, which it should be the element R3. Make sense? So if IB is required as given here, if I ask you how much is the current over this electrical element, as we discussed, we said that it should be Vx over R3, right? So here, IB, and this is the requirement. So just, and this is going to be the like the extra step, is just to find the requirement. What is required in this problem? It is required just to find IB, how much it is. So IB, it should be the Vx over R3 according to this method that we applied. So how much is Vx? Vx is already given by V2 negative V3 over R3, which is already given by 20. So we gonna get it by the V2 negative V3 over 20. How much is V2? We got it here by 13.8 negative 19 over 20. If we did the calculations, we're gonna end up with negative 0.259 ampere, which is gonna be around like IB. It should be the negative 0.6 ampere. So what does it mean, this negative? Okay, this negative, it means that the direction of the current over this electrical element, it should be to the opposite of Vx. This negative indicates that the direction, the current direction is opposite to the Vx direction. What is the Vx direction? This is the element voltage over this electrical element over this resistor, right? So, and this is very clear. Vx, I assume Vx in this direction, goes in this direction, and I got the current opposite to it, it means that the current should go right. And this is what already given. The current is given in the electrical circuit, it should go right, right? And I already got it in the correct direction as given here. Make sense? So this is for the first example. So the procedure is very simple, but it requires some practice over it. Make sense? Now let us move to another example here, which is example 2, which is very similar. So for this electrical circuit, and let us assume that it is required, these are the requirements here, it is required to find the Ix. How much is Ix? Which is the current over this electrical element. Make sense? So the procedure is still the same. The first step is just to locate the different nodes. How many nodes do I have here? We have, this is the first node, we have a second node, we have a third node, we have a fourth node. Then assign one of these nodes to be the reference node. Intuitively, we're gonna pick this one as the reference node. Why? This is the source, right? And it is preferred to pick one of the source ends to be the reference node, which should be the one that is close to the ground. So we're gonna pick this one as our reference node. This is the reference node. Make sense? Then assign voltage to all of these nodes. So we're gonna have like V1, V2, and V3, and this should be the V0, which should be V0 voltage for this ground. Make sense? Then what next? What you're gonna do basically is just to assign or locate the element. This is step 4. Locate the element. We do have one element, second element, third element, fourth, 5, 6 elements, right? One of these elements is a current source, which is this current source with a current of 10 amperes. Make sense? But anyway, forget about this detail for now. We do have these 6 elements. Then assign element voltage to each one. So for this one, which it has one end in the reference, so its element voltage should go. It should move from the reference node to the other node, and it will have a value typically the same as the other node value, which is V1. Make sense? This is also another element, so it's gonna take a voltage that move from the reference node to the other node, and the volt over this one, it should be V2. And there should be another voltage for this element, which it should be V3. It moves from the reference node to the other node, so it's gonna take the value of the other node, which is V3. But how about these other 3? So we got 3 elements. We still have other 3 elements, like this element. So I'm gonna assign like Vy, for example. I'm gonna assign Vx. Again, you can switch the direction, you can give any names, it's up to you. I assume that Vy, this is the element voltage for this element that moves from V1 to V2. The same thing for this one, I'm gonna assume Vz goes in this direction that moves from node 1 to node 3, but Vx moves from 3 to 2. This is for step 5. Step 6 is just to find the element nodes in terms of the node voltage. I'm sorry, the element voltage in terms of the node voltage. How many element voltage that we have to write their equations, Vx, Vy, and Vz, but V1 it is already known as V1, V2 is already V2, V3 is already V3 in terms of the node voltage. But for these 3 elements, we have to rewrite again Vx in terms of its node voltages, the same thing for Vy and Vz. So if I ask you how much is Vx, this is gonna give us the first equation. How much is Vx? Vx, it moves from 3 to 2, so it should be V2 negative V3. How much is Vy? Vy, it moves from 2 to 1, so it should be V2 negative V1. How much is Vz? It moves from 1 to 3, so it should be V3 negative V1. Very simple. Make sense? Then what next? We're gonna move to step 7. That is state that we have to apply the Kirchhoff current law. Kirchhoff current law to all of these nodes, right? In total, we do have 4 nodes. We're gonna skip the reference node as we mentioned, but we do have 3 other nodes. How about the node 1? We can write a Kirchhoff current law to this node because it has no sources here, right? All of these are electrical elements which are resistors. But if you're gonna look to node 2, node 2, it has a current source, right? It is one end of the current source, but this one, it is not a voltage source. We are pretty sure of the current over this branch, it is already 10 ampere, right? So that's why we can write Kirchhoff current law at this moment to node 2. So it means that we can write a Kirchhoff current law to node 2, or we have to write a Kirchhoff current law to node 2. Why? V2 it is not known. I don't know how much is V2, I don't know how much is V1, I don't know how much is V3. So in total I do have 3 unknowns, which are the V1, V2 and V3. This is not a voltage source. If there is a voltage source here and the voltage is already given, it means that you do have a value for V2. But in this case, I don't have a value for V2, neither V1, neither V3. So it means that we need 3 equations. So I'm going to apply Kirchhoff current law to the 3 nodes, node 1, node 2, node 3. Which one that you have to start first, it doesn't matter. Just apply Kirchhoff current law to all of these 3. It doesn't matter which one first. I'm going to start, for example, with node 1. So let us start with node 1. So the Kirchhoff current law, it has 3 currents because it connects 3 elements. One element that enter its current enter the node, this one leave the node, this one too is leaving the node. So we do have V1 over 10. V1 over 10, this is the current. V over R. V over R is the current, very simple. So as you can see that V1 over 10, it entered the node, but Vy over 5, it leaves the node, and the Vz also leaves the node, which is Vz over 20. So it also negative Vz over 20, it should be 0. Then your objective is just replace Vy and Vz by their node voltages. So we're gonna have here, we're just gonna carry on the V1 over 10, negative. How much is Vy? It is already V2, negative V1 over 5. How much is Vz? It is already V3, negative V1 over 20. Then multiply all the terms times the maximum denominator, which is 20. If you multiply, we're going to end up here with 2V1 negative 4V2 plus 4V1 negative V3 negative V1 equals 0. Then your objective is to arrange this equation into V1 term plus V2 term plus V3 term. It is better to arrange this equation in this form because we're going to end up with 3 equations. So you can use the calculator to solve them very quick. So if we arrange these terms together, we do have 2 plus 4 negative 1. This gives us in total 5V1. And for V2, we do have like just negative 4V2 and negative V3 equals 0, and this is going to give us the first equation. How about the second equation? This is going to be for node 2. As for node 2, we do have 3 currents as well. It connects 3 elements. Vy enter the node, V2 enter the node, V3 equal the node, right? Vx equal the node. So we do have Vy over 5, Vx over 10, and the V2 over 10. I'm sorry. Yeah. For this electrical current, I should divide, for this branch, I should divide V2 over a resistance here, right? But I don't have resistance and I don't need it. Why? What is the thing that we sum here? What is the thing that we calculating as V over R? It should be current, and the current is already given by 10 amperes. So what does it mean? It means that we do have 3 currents. One is already given by 10 amperes that enter the node. It goes into the node as given here, right? Just observe this arrow direction. It goes to the node, so it should be positive. But how about if you already given the same electrical circuit, but for some reason the current direction is opposite, so you're going to substitute for this current, it should be negative 10. Why negative? Because it goes opposite to your assumed direction for V2. Again, if the current direction is switched down, it means that this 10 should be substituted down in the Kirchhoff current law as a negative 10. Why? It is opposite to the V2 direction that you just assumed. Make sense? But here I already given the current 10 amperes is already given in the same direction, in a direction which is like it is in the same direction of V2 that you just assumed. Make sense? So it means that you're just going to substitute for the 10 ampere as a positive because it entered the node. Vy also entered the node, so it's going to be Vy over 5, and Vx over 10 also entered the node. So we're going to end up with the Kirchhoff current law to node 2 as Vy over 5 and Vx over 10 and the 10 amperes. So we're going to have the Vy over 5 plus the Vx over 10 plus the 10 ampere. It should be positive. It goes into the node, equals 0. And in the same direction of V2 that I assumed before. Make sense? So this should give us the second equation, but we have to replace the V Vy by V2 negative V1 and the Vx by the V2 negative V3. So it is V2 negative V1, V2 negative V3. So it is V2 negative V1 over 5 plus the V2 negative V3 over 10 plus 10. Then multiply all the terms of this equation times the highest denominator, which is 10. So it means that we're going to end up with 2V2 negative 2V1 plus V2 negative V3 plus 100 equals 0. Then just collect the terms and make the arrangement to have V1, then V2, then V3. So the first term, which is V1, is going to be negative 2V1. Then if you sum the V2, we're going to have like plus 3V2, these two terms, negative V3 equals negative 100 if you just decided to move this one to the other side. Make sense? And this is going to give us the second equation. Then how about the third equation? Because we do have three unknowns, we're going to repeat the same procedure but for node 3. For node 3, we do have here Vx, V3, and Vz, three elements. This node connects three elements, one line, second line, third line. So there are three elements around this node. One element is V3 over 5. The second element is Vx over 10. It leaves, but this one enters, this one leaves. And the Vz also entered the node by Vz over 20. So we have Vx over 10, V3 over 5, and Vz over 20. Okay? So we're going to end up with this equation as V3 over 5 negative Vx over 10 because it leaves plus the Vz over 20. It's positive because it entered the node equals 0. Then we are going to substitute for Vx and Vy. Vx we got it by V2 negative V3, Vz V3 negative V1. If we substitute down here, we're going to end up with V3 over 5 negative. We got Vx by how much? It is V2 negative V3 and V3 negative 1 for Vz. So it is V2 negative V3 over 10 plus V3 negative V1 for the Vz equals 0. Make sense? Then multiply all the terms times the highest denominator, which is already given by 20. So we're going to end up here by 4 the V3 negative 2V2 plus 2V3 plus V3 negative V1 equals 0. Then your objective simply is just to write again this equation 3 in this order. Like we're going to start with the V1 term as negative V1, which should be this term. Okay, so it should be negative V1, negative V2, 2V2. And for the V3, we do have 6 plus 1, so it's going to be 7 V3 equals 0. And this is going to give us the third equation. So at the end, we're going to end up with three equations that you can simply use the calculator to solve them. If you solve these three equations for V1 and V2 and V3, we're going to end up that V1 will be 45.45 volts and the V2 will be 72.73 volts, and we're going to find the 27.27 volts for the V3. So these are the node volts. Make sense? Remember that the requirement in this problem, it is required to find Ix, how much it is. So as for the Ix, it should be the Vx over the 20. It should be it should be Vz over 20. So it should be Vz over 20. So Ix here, which is the requirement, it should be Vz over 20 ohms. We already defined Vz above by the V3 negative the V1 over 20. We got V3 equal 27.27 negative V1, which is 45.45 over 20. If we did the calculations, we're going to end up with negative 0.0909 ampere. So this should be the Ix here direction. So what does it mean, this negative? This negative indicates that the correct direction of the current Ix, it should be opposite to the VZ direction. So what does it mean? It means that the correct direction of the current Ix, it should go in this direction with the same value, which is the 0.9 ampere. So it should be opposite to the given direction here. Make sense? So this is for the example 2, and this is for the node voltage analysis method, which is a very simple method that we can consider it for the resistive circuit analysis. Okay, so that's it for this video. In the next video, I'm going to discuss the last method, which is the mesh current method, how it works. Thank you.